spoke last time, so that's okay. We'll bring the browser back up. Just restore everything from last time. And then we can look at the spreadsheet again. Don't bother to recover. Okay. So the whole idea of a subroutine is about how can we reuse code? Okay, that's the question. How can we reuse code so that you don't have to specify the same logic over and over and over again? Okay. I'll use a very simple example here, but you can probably imagine, what if the subroutine does something a whole lot more complicated. So in this case, in this subroutine, I just want to increment the value of the variable x, and that can easily be done with x gets x plus 1. So the whole point is not, that this is, a simple operation and it can be done without using a subroutine. The whole thing is, what if this is like a 20 line or 40 line kind of logic, and we have to do it from different places of the algorithm. Okay, just kind of imagine that's the situation that we have. When you define a subroutine, it is not going to execute by itself. A subroutine will only execute when you invoke the subroutine. In other words, here is a definition of something that is complicated to do, but it does not get triggered. It does not execute all by itself. You have to say, oh, it's time to perform those operations specified in this subroutine. Then you will go ahead and execute the logic in the subroutine. The big question is, what happens next? When the subroutine is done, what else do you do? Well, the subroutine has to quote-unquote, return back to where you started the whole thing so they can continue execution after the invocation of the subroutine. So let me go ahead and just give you one simple example in this case. We have one global variable x, and we have it initialized to, let's say, 7. And then we'll go ahead and invoke the subroutine increment x. And this is a fairly simple example. It doesn't have any tricks, doesn't have anything that is really that interesting. But we'll use it as the first example to illustrate the mechanism of invoking a subroutine and also how to return from a subroutine. In other words, when a subroutine is all done, what do we do? So let me save the file first. Save to today's folder. And I'll call this simple invoke. And use a new window for the trace. And you can see that problem is fixed. The problem that I had a little bit earlier, not being able to resize the screen, now it's fixed. Okay. And this time we don't need a comments column because there are no conditions to evaluate. There are no print statements. So we can start with line number and one column for our global variable x. So these two columns start existing from the very beginning because one has to be there because in terms of line number, we have to indicate, first of all, what is the precondition of this algorithm. The precondition is we don't need to know anything about x because the first thing we do is to initialize x to 7, which brings us to the first point once your programs have definitions of subroutines. You don't start executing inside a subroutine all by itself, so that means the first line that you start with will be the first line outside of the definition of a subroutine. In this case, we only have one definition of a subroutine, so the first line to start in this case will be line 4. Okay, we start outside of the definition of a subroutine. We do not start inside. Is that okay? Okay, you can kind of look at the definition of a subroutine as a procedure, a manual of procedures. Okay, for instance, let's say you are, since we are all talking about the tsunami and also the nuclear plants, let's just talk about the nuclear plant. Okay, with any nuclear plant, operating a nuclear plant is a very complex process. Okay, there are a lot of procedures to follow. There's a lot of stuff that people cannot just remember. Okay, you don't want someone to walk into a nuclear plant and say, okay, you're supposed to regulate the temperature of the core. Okay, and that person says, well, I can kind of remember, 7 out of the, 15 steps to do this. I'll go ahead and see if I can get it done, okay? You don't want that to happen, right? So what do you want to do? You can fire that person, but the next person who comes along can pretty much do the same thing. So what you do is you keep manuals of procedures, how to do stuff, right? And this is basically what it is, okay? The definition is basically a part of a binder that defines a procedure of how to get something done. But unless your supervisor tells you, oh, you have to go, regulate the temperature of the core right now, to have a manual override, you don't actually go into the manual and randomly select, procedures to perform. And it's the same thing here. The invoke statement is basically the supervisor saying, go ahead and perform that procedure. Then you look up the procedure, in this case increment X, and follow the procedure defined inside the subroutine definition. Is that okay? Okay. So imagine each defined sub as a procedure that is written inside a manual. Okay, it contains all the steps and it spells out exactly how to do something. But we are now on line 4. Line 4 says initialize X to 7. Then we go to line 5, invoke increment X, which basically means look up the procedure called increment X and perform all those steps inside. It's not a hard thing because we can definitely tell that the subroutine starts here and this is what it does. The big question is, what do we do after increment X is done? That's the big question. What do you think we should do? It's done. Okay, the whole algorithm is done, right? Because according to this, there's nothing else after the invoke statement. So we should go to post immediately after the subroutine is done, and that's it. But increment X does not know that. Okay, increment X is a procedure that is enclosed. It's basically on its own. So when the computer is done executing increment X, it really doesn't know what to do unless it can keep track of, oh, okay, I'm supposed to continue execution over there when I'm done. Okay, so we need something. We need basically a piece of breadcrumb to remind ourselves, where to go when we are done with that. Okay. Now, what is the story that has the breadcrumb to remember, how to do something? Okay. Now, did that work? It didn't work, right? Because somebody, something ate the breadcrumbs. But it's basically the same idea. So what we do here is instead of using, breadcrumbs, we allocate a column, in this case column C, and label it as return line number. Okay. Now this is the first time ever that we allocate the use of a column on the fly during the execution of the program. Okay. Before, with global variable X, we just, it starts to exist as soon as the program, executes, and it does not go away until the program is all done. Okay? But when you look at column C, we don't use it until we invoke the subroutine. It is allocated on the fly. Okay? And you will see that if we allocate on the fly, we also have to deallocate on the fly when we are done using that column. Okay. But the name of the column is return line number because it reminds us where to go back to when this invocation is done. In this case, where do you think we should go back to after we increment X? Post. We should go back to post, not line 5. Because if I had written down line 5 here, then we'll be doing the increment X infinitely. Because when we go back to line 5, what does line 5 do? Invoke increment X again. And this way, we'll just keep bouncing between line 5 and line 2, line 5 and line 2, and it will never stop. That's why we have to write down the line that is logically following the line that has the invoke statement. The line that has the invoke statement is line 5. The line that is logically following it is post. Even though there's no line here, it is implicitly our post. So is that part okay? Okay, you allocate a new column. In the new column, you label it as return line number, and then you use that column to remember where am I supposed to go back to when the subroutine is done. That's the first step of invoking a subroutine. The second step is very easy. You look up the actual subroutine and you start execution in the subroutine from the beginning of the subroutine. Okay. Now the other part seems kind of trivial. Start the execution of the subroutine from the beginning. That part seems trivial. It seems to make sense without even having to say it. At this point, it seems obvious, but later on, it will not be as obvious. Okay. The only line in this particular subroutine called increment x that actually does anything useful is line 2. So we'll execute on line 2. That's fairly easy. X gets x plus 1. So basically, we increment 7 to 8, put it back into x, and we are done. And now we execute line 3. Now that's also kind of abnormal in this class because typically we don't track and if, we don't track else, we don't track and while, and so on because they are just marker lines. In this case, it's not just a marker line. And define sub actually has a special meaning because it is saying, oh, I am the subroutine and I'm done execution here. Where am I supposed to go next? So that's why end define sub is not just a marker to mark the end of a subroutine. It also has meaning when you execute the subroutine, okay? Because it's time to do this. It's time to look up the return line number column and say, okay, I'm ready to go back now. Where am I supposed to go back to? Oh, we're supposed to go back to post. Okay, so I'll remind myself that the next line to execute is post. But at the same time, I have no use of column C anymore. And that's why you have to deallocate column C right away and just say that this column is no longer in use, which means if this program is not done at this point, I can reuse column C for other purposes now. Is that okay so far in terms of the concept of invoking a subroutine and also returning from a subroutine to where we started, well, one line below where we started? Is that okay? Okay. So this is pretty much the simplest case of invoking a subroutine. We'll save it one more time, and then we'll talk about the second example. The second example is basically pretty much the same thing, except we invoke a subroutine more than once within the program. So we'll go ahead and start a new spreadsheet for that. And this time we have, well, let's go ahead and do the same thing. Define sub, increment x. So the subroutine is exactly the same as the one before, except this time I will do something like this. X gets the value of 7, just like last time. Then I will say invoke increment x. Then I say x gets x times 2. Then I invoke increment x again. That's the program. In other words, the difference is fairly minor. In this case, you basically invoke it twice. The focus is what happens to the column that we deallocated from the first invocation. Okay, are we going to reuse the same column in the second invocation or what? That's the question. That's the focus of this trace here. So we go to the trace window in sheet 2. Basically, we have the same thing. We have a line number, and then we have the variable x. Now, the line number and variable x, with these two columns starts to exist from the very beginning of the trace of the algorithm, and they last all the way until the end. Okay. In terms of line number, it's the same thing. The precondition is we don't need to know anything about x because on line 4, which is the first line outside of the definition of any subroutine, is to initialize x to 7, just like last time. This part has not changed. Line 5 has not changed from last time, so we can do it fairly quickly. Allocate a new column. Remember where we're supposed to go back to, but this time it's not post. Where am I supposed to go back to? Line 6. Very good. And then we can continue execution in the subroutine, starting with the first line in the subroutine. Okay. So nothing has changed here. On line 2, we just increment the value of x from 7 to 8. We go to line 3. Line 3 also has two things to do. The first thing is to look up the return line number column, which tells us we have to continue execution on line 6. And the second thing it has to do is to deallocate that column to basically indicate that column is no longer in use. Are we doing okay so far? Same as last time so far. Line 6, fairly easy to do. We just multiply the value of x by 2 and then put it back into x. x now has a value of 8. 8 times 2 is 16. We store 16 back into x, so now it is 16. Pretty easy stuff. Then we go to line 7 again. Oh, excuse me. Then we go to line 7 the first time. And line 7 is an invocation of a subroutine. So we do exactly the same thing as last time. Okay, so we have to allocate a column. But since column C is at this point available, we reuse column C. Okay? In other words, when you allocate a column, when you invoke a subroutine, you basically allocate the leftmost column that is available. Okay, so let me say that again. When you invoke a subroutine and you have to allocate a column, you allocate from the left. You pick the leftmost column that is at the time available. In this case, column C is available at this time because these x's here tells us that this column is no longer in use at this time. Are we doing okay so far with the concept of allocating the leftmost available column? Question?
Can you explain what's allocating?
Allocating means using. It's more than just using. Assigning it to
making it available to be used.
Assigning it to a particular use.
I've used that word too often to really remember how to express the meaning. It actually has two meanings. It's not just to use something, it is also to mark it as in use, then you use it.
Like
okay?
setting it aside.
Setting it aside, very good. Setting something aside and then start to use it. Is that okay? Okay. It's kind of not exactly the same. It's kind of like when you walk into a classroom and you want to find a place to sit down and start the class. You're quote unquote allocating that empty seat to yourself so that you have a place to sit down and take the class. It's kind of like that. And then when you leave the class, when the class is done and you leave the classroom, you are quote unquote deallocating the resource that you're using so that the seat and the chair can now, your chair and the desk space can now be used by another student for the next class. Okay, so that's the concept of allocating and deallocating. Okay. So in this case, the column C is now deallocated. It is available again, and it is also the leftmost column that is available. We don't use column D. We don't use column E. We have to reuse column C. Okay. Now it sounds like I'm being overly picky here. How come we have to use column C? I mean, all the other columns are free too. How come we have a rule of only using the leftmost available column? It's because the way we do it in this class is to mirror exactly what goes on inside a computer. And that's exactly what a computer does, is to reuse the last available column. In this case, it's represented by the leftmost column in the spreadsheet. Okay? Are there any questions about this part?
So basically after line 3 just kind of resets it, technically kind of like empties out the column, right?
All it does is to move a little marker to indicate this is where all the available columns start. So it's because inside the computer you don't really mark something as used or unused. You just move a little bookmark that separates the portion that is in use from the portion that is available. And that's basically what a computer does internally. But in a class like this, I just make it kind of visually clear which column is now available. Okay. I suppose you could use grid lines to draw the boundary, but that's a lot more work for me. Because what you can do is you can draw a boundary across, with these blocks here. You can go to cells. This is something that you guys can do when you go home, is to basically use this idea so that it's easier for you to see the boundary of the portion that is in use. But it takes up a little bit more time in the class to do that. Okay, so on line 16, if you look at which part of the column is available, this is the boundary. Okay, so the boundary goes all the way up to here during the execution of the subroutine X. When the subroutine X is all done, the boundary between what is in use and what is not in use goes back to here. But now since we are allocating that column again with a return line number, it extends out again. Okay. But this time, what is my return line number? Where am I supposed to go back to? Post. Very good. And then we can continue execution in the subroutine with line 2. Line 2 is adding 1 to x. X goes from 16 to 17. We go to line 3 again. Line 3 is going to do exactly the same thing in the exact order. The first thing is to look up the return line number column. It tells me to go back to post. I'll go back to post. Then you go back and say, okay, since I have just utilized this column, it is no longer in use, and now it is deallocated. So if I want to follow the same procedure, I will mark the boundary just like last time. That. And over here, since we're at post, basically everything is freed up at this point. So I'll just do one more here. Okay, and just to be consistent, we have the same thing here. I'm not going to change my notes to use this particular method to indicate what columns are in use and not. Okay, but basically that's, you can't really see it that well if you start to do because of the grid lines. If you go to a page preview, it becomes a lot more clear, like that. So do we have any questions about how the boundary between columns that are in use and columns that are available changes during the execution of the algorithm? Any questions? This is the first time we have seen anything like this. Okay, to allocate and deallocate columns on the fly during the execution of a program. Okay, if there are no questions about this, we'll go ahead and close this and save the file first. And I'll name this one 2 invocations because we have exactly 2 invocations, one on line 5 and the other one on line 7. Yep.
Why do you go back to line 2 after you're done with 7?
Because line 7, I'm not done with line 7. Row 9 of the trace is the execution of line 7. This is the first time we get to line 7. Line 7 says we're supposed to invoke increment x. When you invoke a subroutine, there are 2 things to do. One is to set up the column, the return line number column, and then the second thing to do is to continue execution in the subroutine that you're invoking, and that's why we go to line 2. Okay. Any other questions about this particular example? Are we all good? Okay. So I have just saved it, and I can close this one and then start with another spreadsheet. So I'm going to illustrate exactly the same thing yet another time, yet one more time. But this time I have 2 subroutines, and I will just use increment x, just like last time. X gets x plus 1, and define sub. And then we'll have something a little bit different, okay? We'll say increment x 2, which means increment x by 2. And what we'll do is we'll invoke increment x from inside increment x2. Invoke it twice. Like that. And we want to find out what happens when we execute the algorithm in this case. So we'll initialize 5 to 5, and then we invoke increment x2. And just for fun, we'll go ahead and invoke the other one too, just to see whether we can do it or not. Okay. And fix all the indentations first. And give it line numbers. And save it, just in case. And this is called nested invocation. Basically, you have one invocation that is inside the definition of a subroutine. Okay, the focus of this particular example is nothing has changed. Okay, all the stuff that I have talked about, all the rules and all the procedures, the mechanism of invoking a subroutine and continuing after the end of a subroutine, none of that has changed for this particular example. In other words, in the course of today's class, by the end of today's class, I should sound like a badly broken record. Okay, you guys should be saying, Tech, stop. We know that already. Don't repeat that again. Okay, so hopefully that's what you will feel at the end of today's class, because that means you guys have the concept down and nothing is surprising because, oh, it's the same thing. Okay. All right, so let's take a look at this one first. Line number, we have a global variable x just like last time. So the focus is what do we do when the invoke is inside the definition of a subroutine. Particularly, what do we do on line 5, what do we do on line 6, and how does that relate to line 7? Okay, those are the questions. First of all, which line do we start with? The first line that is outside the definition of any subroutine. Which line would that be in this case? Line 8. Okay, so we start with line 8, or we should start with 3 and just say that we don't need to know anything. Then we start with line 8. Line 8 is initializing x with a value of 5. Then we go to line 9. Line 9 is invoking a subroutine. 2 things to do. 1, allocate a column. And remember which line we're supposed to go back to. We're supposed to go back to line 10. That's easy enough. And then step 2 of invoking a subroutine is to continue execution inside the subroutine that you have just invoked. Since we are invoking increment x2, we have to go to line 5. Okay. Is that okay so far? Now, yes.
Why is this line 5?
Because we continue execution on the first line of the subroutine that we are invoking. We're invoking x2, we go to x2 and start execution from the first line inside the definition of the subroutine.
Why don't we go on line 4?
Because line 4 is just a marker, we don't execute that. There's nothing to do on that line. Okay. So we start execution on line 5, and what do we do here? We have another invoke. Do we change the rules or the mechanisms that we have been using for the past 2 examples? No. We do exactly the same thing. So 1, we have to allocate a new column. But column C is now in use, so that means we have to use which column? D. Column D. The leftmost available column is column D. So we use column D in this case and label that as a return line number. And in this case, where do we return to? 6. We return to line 6. Very good. So same thing. We haven't changed anything. And then what do we do? That's step 1 of invoking a subroutine. Step 2 of invoking a subroutine is to continue execution in the subroutine that you're invoking. On line 5, we're invoking increment x, so we continue execution in increment x. So the next line to execute is line 2. Line 2 is pretty easy. It's just an assignment statement. X gets x plus 1, goes from 5 to 6. Then we go to line 3. What do we do on line 3? We have to figure out where to go back to. Oh, but Tech, we have a problem here because now we have 2 return line numbers. Which one should we use? When you return or when you are at the end of a subroutine, you use the rightmost column that is labeled return line number. Okay? In other words, the most recently used or the most recently defined return line number is what you use to go back. So which one would that be? It would be column D. Okay, column D is the return line number that we want to use. It tells us that we have to go back to line 6. So here we mark line 6 here. And then we also want to remember to say that, oh, this column is no longer in use, so it can be reused later on. Do we have any questions about this part here? So the only thing I have to add to what we have talked about so far is when you are at the end of a subroutine, you're at end defined subroutine, you have to use the rightmost return line number that is still active. That's the only part that I have not talked about before, because before this, there's only one return line number at any particular time. This is the first time that we have multiple columns labeled return line number. Does it make sense that we should use column D instead of column C? Yeah. This is called the last in, first out order, or LIFO for that matter. Okay? And you will find that in computer science, most of the time things are in this particular order, last in, first out. Okay? And occasionally you will find first in, first out. Last in, first out in real life. Can someone give me an example of something that is last in, first out in real life?
Work, being laid off.
Being laid off.
Being laid off. Sadly, that is the case, yes. What about when you move and you have a U-Haul truck to load up? Okay, the very last box that you push and then close the tailgate, okay, is the first thing that falls off, when you open up the tailgate. That's last in, first out, okay? If you pack, something like a toolbox first, and you want to get back to that toolbox, what do you have to do? You have to empty out the entire truck first. Okay? What about refrigerators? The normal use of a refrigerator is also last in, first out, because it has to do with the geometry of a refrigerator. You only have one door. Okay? So the last thing that you purchase, that you put into the refrigerator is the most accessible item in the refrigerator. And that's the first thing that you will eat or drink, and consume first. What happened to all that stuff in the back of the refrigerator? You have a mini mold farm back there, right? It has bright purple, green, and brown, and all kinds of colors back there. Okay? So we have a lot of last in, first out examples in real life, and this is last in, first out as well. Okay, this is definitely last in, first out. Okay. Okay, now we're back to line 6. And this is the nice part of having a trace, because at any time we can resume the trace because we know exactly where we are. We also know exactly the state of all the variables that we have at any particular time. So that means, on line 6, we can just go ahead and say, what do we do on line 6? Oh, on line 6, we're supposed to invoke increment x again. Well, this is the same thing as last time, because what we're going to do is to reuse columns if we can. In other words, we are allocating the leftmost available column. Which one is our leftmost available column?
D.
Column D. Okay, column D was in use before, but now it is available again. So that's why we reuse this column. We label it as return line number, and remember where we're supposed to return to. Where are we supposed to return to? The invocation is on line 6, and there is something to do on line 7. So the return line number is going to be 7. Very good. That's the first step of invoking a subroutine. The second step of invoking a subroutine is to continue execution in the subroutine that you're invoking. In this case, we're invoking increment x. We go into increment x and continue execution on line 2. Line 2 is pretty easy. We add 1 to x. X was 6. Now it is 7. Then we go to line 3. Same thing. When we are at the end of a subroutine, we look up the rightmost return line number that is still active or that is still being defined. In this case, it's column D again. It's telling me to go back to line 7. Okay, go back to line 7. And then we have to mark this column as available after this point. Now we're on line 7. What do we do on line 7? Line 7 is the end of the subroutine. So what do we do at the end of a subroutine? Same thing, right? We look up the rightmost return line number. Tell me which column should we use this time?
C.
Column C, because column D is now deallocated. We cannot use column D anymore. Column D is, has these symbols saying that it is no longer in use. So the rightmost return line number that we can use is actually column C at this point. It tells me I have to continue execution on line 10. And after that, I can deallocate this column because it's no longer useful. Now we are back to line 10. What does line 10 do? Invoke increment x. And what do we do when we invoke a subroutine? We allocate the leftmost available column. And which column are we talking about? Column C. We label it as return line number. Remember where we're supposed to return to. In this case, it is post. And then we continue execution in the subroutine, which is line 2, we increment x, which now has a value of 7. We bump it up to 8. We go to line 3. It is the end of the subroutine. We look up the rightmost return line number. In this case, there's only one. Okay, so, and it tells me to go back to post. Once I utilize the return line number column, I say it's no longer in use, and then we continue execution at post, which concludes the trace. Am I starting to sound like a broken record? Good. That's the way it's supposed to. Okay, so we'll save this example, and then you guys will think, well, I don't know about this. You know, if text sounds like a broken, it's going to sound like a broken record for the rest of this class. It's going to be quite painful. Well, trust me, I will sound like a broken record, but in an interesting way, because the next example, there are no more special cases. There are no more special cases about using a subroutine. Okay, once you know how to invoke, once you know how to return, which means, at the end of a subroutine, how to continue execution, that's it. We have just talked about the two basic mechanisms of invoking a subroutine and how to continue after the end of a subroutine. But how can I possibly use up the time of today and just keep talking about subroutines? Well, let's take a look at a kind of interesting case here. Okay. So I'll define this subroutine, and I will just call that subroutine. Oh, let's see. Let's give it a name, M. Okay, just a name. Okay, and this one is a little bit different. Okay, from the subroutines that we have seen before. Now, the kind of statements that you can use inside a subroutine, there's no limitation. Okay, you can use conditional statements, you can use loops, you can use pre-checking loop, you can use post-checking loop. Everything that we can use outside of the definition of a subroutine, we can use it inside the definition of a subroutine as well, with the exception of the definition of another subroutine. In other words, we cannot nest the definition of subroutines so that one definition of a subroutine is inside the definition of another subroutine. That we do not do. Okay? That can be done with only one programming language that I know of, which is Pascal. Every other programming language that I know of does not allow the definition of a subroutine inside itself. Maybe Perl does it too. Perl and even Python may allow that. But in Pascal, that's definitely allowed. Okay. So we have a conditional statement here that says, if x is greater than 0, then we perform the following steps. The following step is first, decrement x by 1, and then we invoke m here, and then we have an else, and then the else says, oh, I don't care. Oh, let's see. Let's not even have an else. Just make this as simple as possible, and define sub. And then we initialize x to, doesn't make sense to make it too big, so we'll just go ahead and make it 2, and then we invoke the subroutine m. Let me fix the indentations first, then we'll take a look at this program before we trace it, just so that we know what it is and what may be confusing about this particular example. Okay, so here we have our subroutine. What do you guys think? Does it sound like something that we can do? We are invoking m from inside m. Yep.
But does it say where to return to? Because if it's more than 0, you're hitting line 4, but then there's no telling where to go. Or like that line 6.
Well, that's a good question. Keep that question, in your mind, as we trace it. Okay? Because that's a good question. The question is, it doesn't seem to show, what to do if x is less than or equal to 0. Is that your question?
Yeah, I guess in the previous examples we were showing that you hitting that m defines sub, it allocates the column, and it should tell you where to return to.
Correct. Yes.
But once within the subroutine, it doesn't show where to return to.
Okay, so keep that question in mind, as we trace it. That's a good question. When I saw something like this the first time, I see recursion, I was going like, how is that possible? Because on line 4, we haven't seen the end of the subroutine yet. how can I invoke the subroutine when it's not done? It's not all done yet. That was the question in my mind when I first saw recursion. This is called recursion. When the subroutine calls itself, it is called a recursive call. Okay, a recursive invocation. For those of you who watched Star Trek: The Next Generation, this is kind of like a holodeck inside a holodeck. Okay, that's the kind of stuff that we are talking about here. Okay, let's go ahead and do it. Okay, and see what happens. Okay. The funny thing about this example is, as mysterious and kind of messy as it looks at this point, when we actually do it, I will sound like a broken record again. Okay, we just have to do it one step at a time and use all the mechanisms that we already know. Okay, there's nothing special about this example from the perspective of tracing it. Okay, to come up with an algorithm like this is not the same thing. It's actually fairly tricky to come up with algorithms like this, but to trace one is no different from tracing the other examples that we have done already. Okay, so we'll start with the precondition. Same thing as before. The precondition is we don't need to know anything about x, so we'll just put a question mark here. And then the first line that we should execute is which line?
7.
Line 7, because line 7 is the first line that is outside of the definition of a subroutine, and that's going to initialize x to 2. Then we proceed to line 8. Line 8 is invoke m. At this point, nothing is mysterious. It's just a regular invoke statement. So we'll allocate the leftmost available column, which is column C at this point, label it as a return line number column, and then say when this invocation is done, we go to post. That's it. Okay. Then we proceed on the first line of the subroutine that we are invoking. Remember that step? That's the second step of invoking a subroutine. So which line should we go to? Line 2. Now we do have conditions to evaluate, so we'll just go ahead and insert a column for our comments. And in this case, line 2 is asking a fairly simple question. X is greater than 0 is it's true because it has a value of 2. So we go into the conditional statement. We go to line 3. Line 3 is pretty easy. We decrement x by 1. It was 2. Now it is 1. Then we go to line 4. Ooh, tag, this is kind of mysterious. What do? We are invoking m from inside m. We do the same thing as before. Okay, we just follow the 2 steps again. What are the 2 steps again? First, we allocate the leftmost available column and then label it return line number. Okay, we can do that. Which column should we use this time? Column E. Okay, we label it as return line number. And then we indicate the line number of the line that is logically following line 4 in this case. It's not line 5. Which line logically follows line 4? Line 6. Okay, because we don't track and if, but we do have to track line 6, which is n defined sub. So in this case, we have to write down line 6. Okay, and then we continue execution inside the subroutine that we're invoking from the first line. So where are we supposed to go here? Okay, which subroutine are we invoking? We're invoking m. We only have one subroutine in the entire program. And what is the first line of the subroutine m?
2.
Line 2. So we go back to line 2. Did I change the rules? No. It's the same rules. But this time when we go to line 2, x now has a value of 1. 1 is greater than 0 is true. We go to line 3 again. We decrement x from 1 down to 0. We go to line 4 again. Line 4 says we want to invoke m. What do? Same thing that we have been doing for the past 45 minutes or so. Okay, we allocate the leftmost available column. Which column would that be? Column F. We label it as return line number. And then we have to remember logically which line follows line 4. Line 6. Okay. And then we continue execution on the first line of the subroutine that we just invoked. Which line would that be? Line 2. Okay. Line 2 is the first line of the subroutine that we're invoking. Same thing as before, okay? But this time x is greater than 0 is, x has a value of 0, 0 is greater than 0 is false, okay? Well, I don't have an else with this conditional statement, so we're just going to skip the entire thing and go straight to line 6. Is that okay? Is that something that we have seen before with a conditional statement that has no else? Yeah, we have seen something like that. I mean, basically there's nothing to do when the condition is false. So we go to line 6. Okay, so that's not that's not even related to subroutines. It's just the property of a conditional statement. What do we do on line 6? On line 6 is n-defined sub. So the first thing we have to do is to locate the rightmost return line number that is still active. Which column are we talking about?
F.
Column F. Column F tells me that we have to go back to line 6. So we have to copy that 6 over here. It may look confusing to you, but all we are doing is to blindly follow the mechanism when we're at the end of a subroutine. Okay? If it tells me we go back to line 6, we go back to line 6. Okay. And then we have to deallocate column F. Okay, so column F is no longer in use. We just say that it's no longer in use. And now we continue execution on line 6. What does line 6 do again? It's the end of a subroutine. So what do we do? We look up the rightmost return line number column. We cannot use column F anymore because it is no longer in use. So which one is still in use? Column E is still in use. And it tells me to go back to line 6 again. And then we have no use of column E anymore. And then we deallocate it. Okay? And we're back to line 6. What does line 6 do? We look up the rightmost return line number, which is column E this time. It tells us to go back to post. So we'll go back to post. But remember, we have to mark that column as deallocated at this point. Then we continue execution at post, which basically means we're all done. Okay? That's recursion. That is recursion. Are there any questions about this trace? First of all, did I use any mechanisms, any brand new mechanisms that we have not discussed before? It's all the same stuff that we have talked about before. Okay? Now, recursion is an interesting topic because even with 4-year universities, a lot of times they don't talk about recursion until maybe the last week or so of an entire semester. And yet we are talking about this in week 8. That's because recursion is not special. There's nothing special about recursion when you trace it. It is special from the perspective of coming up with an algorithm that is recursive. But from the perspective of just following an algorithm that is given to you, it's not special at all. Does everybody understand what I'm saying? It's kind of like saying, we have been driving, gasoline type of car for, many decades now, okay? Many decades. When did they first come up with Model T?
1920s.
1920s. So almost a century, almost an entire century. We have been driving, cars that have gas engines, okay? But you still have, and these days it's mostly automatic. So you get in the car, you start the engine, you press the accelerator, it goes faster. You press on the brakes, it slows down, and that's about it, okay? And that's from the perspective of tracing. Now I give you a full electric car. What has changed? Nothing. Okay, you drive an electric car pretty much exactly the same way. So from the operator's perspective, to trace it is almost exactly the same. Whether it's an electric car or whether it's based on the gasoline engine, to you it's all the same. With only one exception, you can quote unquote idle your electric car inside your garage with the garage doors closed without any danger of carbon monoxide poisoning because there's no combustion. Okay? But other than that, from the perspective of driving the car, it's all the same. Now, but what about opening the hood from the engineer's perspective, the guy who's designing the engine? It's all different. Okay? And that's why I said, from the perspective of coming up with an algorithm like this is quite different from coming up with a normal algorithm. But from the perspective of driving, to use it, to trace it, it's pretty much the same thing. Okay. Does this remind you of a loop? A little bit, maybe? Because because if you look at the line numbers 2, 3, 4, 2, 3, 4, and if you look at the value of x, it goes from 1 to 0. It looks kind of like a loop, and that's actually right. Okay, you are absolutely right that recursion is related to loops. Okay, there are programming languages out there that has no loops. That have no loops. Scheme is one, Lisp is the other one. Anything that's based on Lisp has no loops. So the only way they can perform iterations is to use recursion. Okay. In fact, when you take other classes, you will realize that anything that has recursion can be turned into something that does not have recursion but a loop. Anything that has a loop can be turned into something that does not have a loop but have a recursion. They are equivalent to each other in terms of how expressive the mechanism is. But something is better when it's done recursively, and something is better done when it is non-recursive, or we call that iterative. Okay. All right. Well, at this point, let's go ahead and detour a little bit and just talk about recursion. And why do we even want to talk about recursion? What kind of stuff in real life is recursive? So before we do anything like that, we'll go ahead and save this file. Okay, we'll call this recursive invoke. Yep, go ahead.
Like when we go into 360, how would we be able to like differentiate like what to use as far as like recursive subroutine or like algorithms like a if statement?
Okay, okay, that's a good question. The question is, I'm just repeating it for the microphone's sake. The question is, when you go to 360, and how do you decide whether to use a recursive approach or use a loop instead? The answer is quite easy. If you can get away easily with a loop. That's pretty much it. Okay, because recursion does involve some additional considerations. What if because if you think about it, every iteration of a recursive algorithm consumes one more column. Okay. In this case, we have 3 iterations. In other words, we go through the thing 3 times, and you can see that we allocated the columns 3 times. So if you have something that has like 32,000 iterations, it will take up 32,000 columns in this class. But each column represents memory resources on the computer. So that's why recursion is not exactly a very efficient way of doing things.
But the loops, it would be taking up any
yes.
sort
If
of
you
memory along
this
those lines?
exactly, if you did this with a loop, you would just be using one column for x, but you won't be allocating anything in addition to x. Okay. But there are things in real life that are recursive in its very nature. Okay, so we'll go ahead and talk about one example that every school will use that as an example to illustrate what is recursive in not in nature but in in math and other types of problems. It has to do with factorial. Now, does everybody understand what is factorial? Okay, no, yes, kind of, no, okay. I can give you one example. For factorial, we use the exclamation point as the symbol for factorial. 4 factorial is nothing more than 4 times 3 times 2 times 1. That's 4 factorial. Okay? And you can probably imagine what is 6 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Okay? That's factorial. But factorial is also recursive. You can define factorial recursively, because what you can do is to say n factorial equals to 1 if and only if n equals to 0. Okay, this is what we call a base case. 0 factorial is defined to be 1. After this, you can define n factorial as n times n minus 1, the factorial of n minus 1, if and only if n is greater than 0. That's it. That's the definition of n factorial. Does that make sense? In other words, you look at 4 factorial. Can you rewrite 4 factorial as 4 times 3 factorial? Does this part look like 3 factorial to you? It is. Okay? So this is one, commonly used, definition that is recursive, in itself because, that's the definition. There are other applications of recursion too. Remember binary search? Stuff that we talked about last Friday. It's recursive too. Okay. Now, what do you mean by recursive? Well, remember you have a big old pile of sorted cards. Okay, it has to be sorted. You pick out the middle one, and you can throw away either the first or the second half. What do you do with the half that is remaining? The same thing. Okay. So it is also recursive. You can use a recursive algorithm to solve that problem. Okay. What about in nature? What kind of thing in nature has a recursive pattern? There are quite a few things in nature that are recursive. In other words, you want to look at something, but when you try to look at more details of that something, you see the same pattern or the same structure again. If you just look outside the tree, it's recursive. Because when you look at the branch, you follow the branch all the way to the fork of the branch. Okay? You follow one of the branches. What does that branch look like? Just like the branch that you came from, except it's smaller. Okay? Then you run to the end of that smaller branch and you pick one of the many directions that you can go. What do you see? Something that is similar except it's smaller. So it keeps getting smaller and smaller and smaller until you get to a leaf. Okay, because at that point it stops. Okay, and that's recursive too. What about inside a file system? Okay, I should have used this as an example first, because it's actually one of the most intuitive example that we can illustrate. So we go to a file system. This is the file system. Okay. And we have lots and lots of folders here. So let me pick a folder that definitely has a lot of nesting going on. Let's say users, okay? What do you normally see inside a folder? More folders and or files, individual files, okay? So we double click on users and what do we see? Folders and one particular file. Let's go ahead and pick one of these users. Okay, we'll pick 152 user. What do you see? More folders, and possibly some individual files. We click on one of these things, what do you see? Am I sounding like a broken record? But that's recursive. Because when you look into one thing, one component, you see the general structure that you see from the outside again. Okay, so this is also called a self-similar structure. Basically, when you use a magnifying glass to look at something, to look into more details, what you see under the magnifying glass looks like the thing that is not magnified in terms of structure. Okay, and that's basically what recursion is really good at, is to process stuff like that. Okay. Are there any questions at this point about recursion or the concept of something that is recursive? No questions? Okay. Now, before we take a break, I'll just kind of do a little digression on factorial, because even though we have a mathematical definition of factorial at this point, what is the whole point of factorial? I mean, it doesn't seem like it's useful at all. Well, let me tell you one thing. It's very useful when you want to calculate, should I buy lotto today? Okay, that has to do with factorial. Okay, how many people know the rules of lotto? Nobody? Okay, so how many numbers do we play, let's say super lotto?
Like 5 plus 6.
Okay, 5 numbers and then plus 1, right? 5 plus 1? Okay, so we'll write down 5 plus 1. And how many numbers do we have to pick from with the first 5 numbers?
56 or 52.
Okay, so 1 to 56
I would say 56.
or 52?
Google it.
I don't have to Google it. I can go straight to the Lotto website. California Super Lotto. That's Google. And then they have the rules, they spell out the rules too, because I think legally they have to spell out the rules. Okay, come on, move. Okay. Let's pick a Mega Million Lotto, okay? The payoff is $201 million. That sounds like a lot of money. The question is, what are the chances that you will win when you play that game today?
1 in 18 million.
1 in 18 million. But let's find out whether that's really the case, because just because they say that doesn't mean that's always the case, right? So we'll go to how to play, and it spells out all the rules. And let's see, 1 to 56, and then the last number is 1 to 46. Okay, fine. So we'll go ahead and do some calculations here. Okay. So the first number has 556 choices, right? Because before we pick the first one, we have 56 choices. So the first ball, or the first number, has 56 choices. But once we pick a number, the second one doesn't have 56 choices anymore. We only have 55. And then we have 54, and then we have 53, and then we have 52. Those are the first 5 numbers. Okay, and then we have the last number, which is 1 to 46. That one has exactly 46 choices. Okay. Now, but this is not the entire number. This is actually more combinations that we need to know, because in a lotto, the order of the number is not important, is it? It's not important. So let's think about how many times you can reorder, let's say A, B, C, D. If I want to reorder these 4 letters, how many combinations can I have just out of A, B, C, D? Well, let's think about it. For the first letter, I have 4 choices. Of the second letter, I have 3 choices. Of the third letter, I have 2 choices. And the last one, I only have 1 choice, because once I have set the first 3, the last one, there's only 1 choice left. Does that make sense? Okay. So that means, of these many choices, I have to remember to divide 5 factorial from it, because the first 5 numbers, there are 5 factorial ways to reorganize the numbers, but since order is not important, we have to say, oh, they're all the same, and by dividing 5 factorial, I take that into account. Okay? So we now want to take a look at, the chances, how many of these, permutations do we have, when you buy lotto. And for that, we can use, let's say, use a spreadsheet here, because, remember, a spreadsheet is good at what? Calculations, right? So we can say 56 times 55 times 54 times 53 times 52 times 46, and then the whole thing divided by 5 factorial. I think it has factorial. I just don't know whether it is spelled out as factorial like that. No, it is not. Okay, say insert function and find factorial. FACT calculates the factorial. Okay, that's what the name is supposed to be. Sometimes they abbreviate and sometimes they do not. I don't really like it. This is basically the number of permutations that we have, which is 156 million combinations. Okay, so let's go back to the website, because I do want to talk about gambling and stuff like that, just to explain why I do not do it.
Yeah, because the odds
okay,
are not as good as
so you look at this number here and go, but Tack, that's better than 180 million, because it's potentially a gain to do it. But if you look at estimated cash value, it's only 128 million, because Uncle Sam wants his share. Okay, fine. Okay, but let's just say that the estimated cash value is 200 million itself. Is it worth playing the game? Because that has taken tax into consideration. Well, it's still not good enough to play the game, because what are the chances that you are the only person who buy that particular number combination? Probably very slim. Go ahead.
I did 1 in 175 million.
Right, but different people can buy the same permutation. Okay, and many times, when the number, when the payoff is big, you have multiple people buying exactly the same permutation. So now you have to split you have to split the cash amongst everybody who buy the ticket. So that means you have to take into consideration how many tickets in general will be sold for a particular payoff. Okay, because that determines whether how many people will basically have to share the prize money with you on the average. Okay, so in the end, if you do all the calculations, it's not even worth doing it. Okay, that's just the way it is. Okay, now if you buy lotto because I just want to try my luck today, for $1 or something like that, that's okay. But I will not bank on it, and say I want to retire, by buying lotto. That would not be. Yep.
I was reading somewhere that you have more chances of being hit by a lightning twice on a sunny day than winning the lottery.
That's probably believable. Okay. Well, that's why if you think about it. Okay, let's not even talk about math. Okay, if you don't talk about math, and just think about logistics. Okay, think about just reasoning, logic. Okay, what are the chances that you can walk away from a casino with more cash in your pocket than when you walk into the casino? It should be almost next to nothing, or should be zero, right? Because how else can the casinos afford all the splashy stuff, all the food and all the air conditioning, if not anything else? Okay, so on the average, people have to be losing money to the casino in order for a casino to make money, or to even break even. Okay, because there are operating costs. Okay, even if they're not turning a profit, they still have to pay for the electrical bills, building maintenance, and all kinds of stuff like that. So that's how I look at gambling in general. But in terms of lotto, it's easy to calculate the chances. Yep.
Well, then doesn't that mean that human nature is pretty dumb to begin with? If you know you're going to lose, you're walking to lose.
I think all animals are like that. They found out that reward is good, but random reward is even better when you want to kind of control the behavior of just about any animal. Or I think it works better when it is punitive. Okay, when you want to punish something, if you punish something because or consistently when it does something, it knows how to deal with it. It's like, okay, I just won't touch that. Okay, because every time I touch that, I got zapped. Okay, but if it is random, then the animal goes haywire because there's no pattern to it, right? So now it goes like, oh, I don't know what to do. If I touch it, sometimes it gives me food, and when I touch it some other times, it zaps me. What am I supposed to do? Well, there's an easy answer.
You're going to hit it, right?
There's an easy answer, right? You tell the other animal to touch it, and you just stand by, getting ready for the food when it comes out. If it zaps the other animal, you just kind of laugh, right? Just, okay, but I just want to illustrate, why Factorial is a useful thing. Okay, and the funny thing is, Factorial also increases very, very rapidly. Okay, what is 100 Factorial? What do you think is the order of magnitude with 100 factorial? Now we know 5 factorial is what? 5 times 4 times 3 times 2 times 1, which is 120. Okay? We know 6 factorial is 720 because it's 120 times 6. So we kind of know the general trend of how factorial increases. What do you think is the order of magnitude in terms of 10 to the power of something of 100 factorial? In other words, if I have 100 things and I want to see how many combinations where the order is important, how many ways do I have to reorganize only 100 items?
More than a graphic calculator can count.
Well, fortunately, the calculator that I have, gives me a lot of digits, so I can actually go through that calculation. So we want to figure out what is 100 factorial. Okay, I think we have to say factorial of 100.
That next height.
I think it's expecting a parenthesis, maybe.
Keep typing fraction. Yeah,
Oh, okay,
that's
factorial. Never mind. Operator error.
What is the button with the exclamation mark?
Yes,
Oh,
the
okay.
the
Must be the exclamation mark. Where is it?
Right, it's above.
Go over 2 more and then up twice.
Yeah.
Okay, there we go. There we go. That's the number. Well, that doesn't seem too bad, except, you see the scroll bar.
Oh my gosh.
That's 100 factorial. So what that means is if you have 100 cities that you have to visit, okay, 100 stops like for a UPS truck, and you want to figure out what is the best way to traverse the 100 stops, this is the number of combinations. This is the number of different ways to traverse the 100 points when you drive that UPS truck. And that's only 100 stops. So that means, in order to optimize the truck route for a normal UPS truck, which probably has close to 100 stops every single day, is an intractable problem. Because to find the optimal solution, you actually have to evaluate every single one possible combination and then pick the one that has the shortest, that has the least cost. It's not always in time because fuel is a consideration, toll is a consideration, and so on. But in order to evaluate which one is truly the optimal path, you have to consider this many combinations. And that makes a lot of optimization problems. We call those intractable problems. Okay? Just because the number of combinations increases so rapidly. Okay? Are there any questions at this point before we take a break? No? Okay, let's come back here by 9:32, and then we'll continue to talk about other stuff that is related to subroutines.